Okay, so you got your horizontal rows are called your periods, your vertical columns are called your groups. It's probably one of the coolest labs we'll do all year. So what I'll do is we'll do it tomorrow. We'll do something else today while you guys are at PSAT, and we'll flip-flop it. I'll do the lab tomorrow with you, and we'll do the periodic people thing today. Okay. All right. In a group, which are these vertical columns, and I know we've said this before, okay, group 1, they all have one valence electron. What this does is it allows these elements that are in group 1 to all have similar chemical properties. I don't know why there's a little bullet point here, but there is. Probably hit an enter after that. Okay, this is very important. Because a lot of times the question will be, which of the following elements have similar chemical properties? What are you going to be looking for? They're going to be in the same vertical column. Okay. We know that they have the same number of valence electrons. They also have similar chemical properties. All right. Side trip. Have you ever cooked string beans or broccoli? Okay? And what happens when you put those string beans or broccoli in the boiling water? They turn what? Say it again? They do get soft. But before they even get soft, do you notice something happening to them? They turn bright green. And then if you leave them for a long period of time, and you cook them and cook them and cook them and cook them, what happens to them? Oh, you guys got to get in the kitchen more. They turn like a olive green. They get like a brownish green color. Did you ever notice that? No? Well, they do. And the reason why they do that is because calcium and magnesium switch places. So when, I think it's magnesium, when magnesium is in the broccoli, it gives it a bright green color. When it switches with the calcium, it gives it a olive green color. It's because these two elements switch and the color changes in the actual broccoli. We, right before the holiday, we will probably, I'm going to say probably, because I don't know 100%, watch a movie called Radium Girls. Have any of you seen Radium Girls? The radium, I'm sorry, I'm having trouble talking, but the Radium Girls look like this. Okay? This is the movie. This is the real life Radium Girls. This is the movie. This is one of the girls. So these girls worked in the American Radium factory in New York and New Jersey, somewhere in the Northeast. I can't remember exactly where. And they used to paint the watch dials for the soldiers overseas. And they used a uranium-based paint. Well, the uranium glowed. It was discovered by Madame Curie. And it glowed. Now, look where radium is on the periodic table. And look where calcium is on the periodic table. Well, this radium, not only was it radioactive, which we're going to have to write down in a second as well, but not only was it radioactive, but it replaced the calcium in the girls' bones. And so the bones of the Radium Girls basically just crumbled and they fell apart. Let's see if I can find. There we go. And it was located in the same group as calcium. So it was switching places. Just like the barium, the magnesium and the calcium switch places when you cook your string beans. Next time you watch somebody cook string beans, you're going to think of me. Okay? All right, let's name the columns of these groups. Group number 1. Actually, I'll put this up after I tell you what they are. Group number 1 on the periodic table are called the alkali metals. So lithium all the way down to francium or francium. Okay? These are called the alkali metals. I'll put that slide up in a second. Let me just tell you what the names are. The next column right here, column number 2, group number 2, are called the alkali earth metals. Now, the alkali metals and the alkali earth metals are highly reactive metals. Those are the metals that when you walk down the street, you're not going to see them laying on the ground. They are going to form salts very easily. They're going to react very easily with other things. So you're never going to see these alone in nature. And the reason for that is because they only have 1 or 2 valence electrons, and they want to lose them as quickly as possible. Now I'm going to ask you a question. I want you to think before you say anything. Okay? Out of these 2 groups, the alkali metals and the alkali earth metals, or the alkaline earth metals, out of these 2 groups, there's one metal that is the most reactive. Which one do you think it is, and why do you think that is? Which metal do you think is the most reactive? Think about what a metal needs to do to be reactive. It needs to lose its electrons. Which one is the most reactive and why? We have a wild guess?
Francium.
Why?
Because in 7th grade, we watched something that if francium was put in water, there'd be a really big boom.
Okay, now, who was your teacher in 7th grade? Mr. Endres. Yeah, he loved that demonstration. And I had a problem with Mr. Endres only because I would say to him, Mr. Endres, why would you tell them there would be a big boom? By the way, you're right. But why would there be a big boom? What is the science behind that big boom? What is happening there?
It's the most radioactive energy.
Well, it is radioactive, that's true.
But it only has 1 electron.
It only has 1 electron. And in order for a metal to be reactive, it needs to do what with that 1 electron? Get rid of it, right? It needs to get rid of it. Okay? So lithium has 1 electron, and francium has 1 electron. Why does francium get rid of its electron faster than lithium? Go ahead, Alex.
It's in a higher energy level?
It is in a higher energy level, which is essentially further away from the nucleus, right? And so if I draw, can I draw this? If I draw lithium, I'm just going to draw a dot for its nucleus. Let's draw lithium. And lithium has 2 electrons and then 1 electron. Okay, I just didn't draw it all the way around here. It's the same thing. Okay, just because it will be. And here's francium. And francium has 2 electrons and then 8 electrons and then 18 electrons. Can somebody read me the electron configuration for francium? You have your reference tables in front of you? Okay. Give them to me so I don't have to look. 2, 8, 18, 18, 32, 18, 8, and 1. Now notice that there's 7 of these rings, right? There better be 7. 1, 2, 3, 4, 5, 6, 7. Because it's in the 7th period. It's in the 7th period here. Here's the 7, right? All the way across. 7th period. Now, here are all the positives. They're in here. This electron is being held on by that positive. This electron is also being held on by that positive. However, all these electrons that are in here are shielding this last electron. They're like covering it. So this electron is able to leave more easily than this electron is able to leave. So francium is more reactive than lithium. They're both reactive. But out of those two, francium is more reactive. Do you understand why? Okay. Alright, then we get to, so we have alkali metals. We have alkali earth metals. Sometimes you'll hear them called alkaline earth metals. Have you ever heard the word alkali before? Mm-hmm. Where? Alkali water. It's basic water, right? It's more on the basic side if you touch the pH. That's because anytime you have these guys over here, they will form a base. Calcium hydroxide is a base. Magnesium hydroxide. Sodium hydroxide. Lithium hydroxide. Those are going to be your bases. Alright, 3 through 12, this section of the periodic table is a special name for them. These are called the transition metals. They are transitioning from very, very highly reactive metals to less reactive metals like copper, silver, gold. These guys are not reactive. Zinc. They're getting less and less reactive as you go this way. These are called the transition metals. You're going to write down in a second transition metals. But what happens with the transition metals that makes them so special is that when they are in a compound, they have beautiful colors. Yellow, blue, green, purple. My favorite one, manganese. We don't have it anymore, but we used to have manganese here. Manganese is a beautiful purple color. What about iron? What color is iron? When it's react in the salt. What's that? What color? Green. Think about what iron does. It's like an orange-red color. Okay? You know copper's color. Statue of Liberty. What color is it? Green. Okay? So all these guys have specific colors. Now, we get over to groups 13, 14, 15, and 16. We are not going to name these groups. Okay, boron, carbon, nitrogen, and oxygen. We're just going to call them the boron group, the carbon group, the nitrogen group, and the oxygen group. Group 17 are called the halogens. The word halogen is called a salt former. They form salts with these metals that are over here. Now, out of this group 17, which one is the most reactive and why? Think about what the halogens want to do. Do they want to lose electrons or do they want to gain electrons?
Well, reactive because the electrons are closest to the nucleus.
Very good. The fluorine is the most reactive because those electrons in that second energy level, second ring, are closest to the nucleus. So that nucleus has a lot of pull on that second ring because it's pretty darn close. So this is the most reactive metal. Fluorine, all the way over there, is the most reactive nonmetal. Why do you think neon is not the most reactive nonmetal? Go ahead, Alex.
The energy levels are so.
Completely filled valence shell. So it is not reactive. So if they ask you about energy level, if they ask you about reactivity, which they will,
you're going to not pick group 18. Hello. That's all right. What's up? Yeah, sure. He's on his way. Okay, bye. James, Mr. Sharuvas needs you. Okay, so you always want to keep in mind that we're not going to pick that last row. The last column, the last group 18, for if they ask you for the most reactive. Because that group is called the noble gases. And the noble gases don't react. They have full valence shells. Okay? So keep that in mind. What happens to the reactivity as you go this way? More reactive. What happens to the reactivity of as you go this way? More reactive, okay? But for different reasons. Here, we are the most reactive because we are losing electrons. Here, we are more reactive because we are gaining electrons. Okay, another question, and this is another common question. What happens to the metallic character? That means how metallic it is as we go from right to left. Do you get more metallic or less metallic? More. You get more metallic as you go this way, because this is where all your really, really, really hardcore metals are. Okay? As you go from left to right, you get less metallic. Okay? That's not reactivity. That's just if you're metallic or you're not metallic. Okay? Now, that's very easy to see, but what happens if you go from top to bottom? What happens to the metallic character? These are all metals. All these suckers are metals. Do you think you get, hold on, don't move. You get less metallic as you go down or more metallic as you go down?
Less.
More. And you're not leaving me, are you? Well, some of you are. Okay, now look, you can see it right here. Non-metal, metalloid, metalloid, metal, metal. See how it's getting more metallic as you go down? So over here, even though they're all metals, you're getting more metallic as you go down. All right, you guys going to PSAT thing?
Yeah.
Okay.